Okay, so our first item of business for tonight is the test that we took last week. Those of you here in the right state can obviously pick it up from me. The other sites, you should have got it. You should have received it back in an email sometime in the last couple of days. If you have not received it back yet, please send me an email and I will resend it to you so you have it. With the tests, once you have them back, you're allowed to do corrections. And what corrections involve is redoing the problems. I'll get yours in just a second. Redoing the problems you got wrong. And now, unlike the original test where you didn't have to show work, where I didn't punish you if you didn't show the work, when you redo them, you do have to show your work. And then you can turn those back into me, and I will give you, or you will earn, if you have them correct, up to half your points back. Now, there's no restrictions on what you can do to get these. You can work with others. You can work together if you want to. You can ask a teacher, someone outside the class. You can come to me and I will sit down and work through all of them with you if you want. The purpose is to make sure you have the correct answers down and the correct process down for those problems you didn't get. So please make sure, if you're not absolutely sure that you have them right when you redo them, please ask me, and like I said, I'll be more than happy to sit down and work with you. So what that does is, let's say you had a 70% on the test. Corrections bring that up to an 85%, which would actually be a B-. So that makes a huge difference. An 85 would go up to a 92.5. A half point would mean that you made a mistake. The answer is incorrect, but it's a common mistake that I see a lot. So I knew what you were doing and I knew your thought process was. So it might be maybe you found the wrong thing. Maybe you had to subtract it from the total to get the answer you're looking for, or something like that. You had the right process, you just didn't finish it, or somewhere along that lines. So again, those of you at the far sites, you don't have to write it on the page and rescan it if you don't want to. By all means, you're welcome to do that if that's easier for you. But if you only have a few problems wrong, you can just send me an email and just kind of type it out in the email, and that'll earn your correction points. Just whatever you do, don't just turn it in with the correct answers on it, because I won't accept that. Nope, I haven't said anything about how long you have yet. Usually I give you a couple of weeks. One reason for that is I won't answer questions on it tonight, because I want you guys to at least look at it and think about it first. But next week I'll be more than happy to answer any questions you still have on the tests. Yep, you can take those home. Those are yours. Hang them on the fridge. Yep, just do it right on there and turn it back in. Yep, do it right on that test, or like I said, send me an email if you want to. But those are the questions. Yeah, just redo those. Generally, my hard cutoff, I prefer to have them within about 2 weeks from today, which would be, I think, like March 5th, something like that. My absolute cutoff on corrections is once we hit the next unit test, I won't accept them anymore. Okay, now my next warning, and this is just from years of having this happen. Unit 1 is kind of a review and prep. Many people, and I have it happen every semester, I'll have 4 or 5 students in the class do fairly well on this first test. And then they think, okay, this class is pretty easy, I've got it. I'll warn you, it gets a lot more difficult very quickly starting here in Unit 2. For those of you coming into the room at the other sites a little bit late, we mentioned you should have your tests back. If you don't have yours back, make sure you send me an email and I will resend it to you. You should have received it in email in the last couple of days. Redo the problems you got wrong, and this will be in the recording. You'll have to get the details off the recording or ask me on breaks or something. Redo the problems you got wrong and resubmit those, and you can get up to half your points back. So very important to make sure you do that. So like I said, Unit 1 was very easy, and every semester I have a few students who will do very well on the Unit 1 test, and they'll think, I've got this, I don't have to put so much effort into it. They'll start missing classes or whatever, and things fall apart, and that second test comes around, and it's kind of a shock. So hopefully you continue to do very good work, but don't let that first unit lull you into complacency, because the material does get a lot more difficult very quickly here. Not trying to scare you, but just a word of caution. I'm a math teacher. I'm scary enough even when I'm not trying. So anyway, tonight we start our Unit 2. And Unit 2 has 2 sections to it. The first section, which is 2 weeks. So that'll be week 5, which is this week, and week 6, which will be next week, on statistics. That's just a very light view of statistics, because to do statistics well takes about 2 semesters worth of a class. And we are not going to invest that kind of time into it. And then the second part of Unit 2, which are weeks 7 and 8, are merchandising. Yes. And then, so tonight we're going to start with the statistics part of it. So let's start out with a little bit of vocabulary. Part of statistics is it's almost like a foreign language. It has its own vocabulary. So we'll start out with the most important thing in statistics is a population. Now, a population is a group of people or things that we want to learn about. Technically, I suppose I should say about which we want to learn, but this isn't an English class, so we aren't going to worry about it. But it sounds like a pretty simple concept, but it's not always as easy to define as you might think. For example, let's say we want to learn about who's going to win in the next governor's election. I know it should technically be gubernatorial election, but I can't spell gubernatorial, so we're going to say governor election. At first thought, you might be looking at it and say, well, we want to learn about the candidates because we want to know which one of them is going to be governor. But that's technically not it, because what we really want to know is who's going to get the most votes. Well, it's not the candidate. Well, the candidates do have something to do with it, but it's not the candidates who get those votes. It's the voters who cast those votes. So what we really want to learn about is the voters. Now, you might be tempted to say all registered voters in the state, but that's technically not true either. The only ones we care about are the voters who will vote in that next election. That's our population. That's who we want to learn about. Now, there are 5-point-some million people in the state of Wisconsin. We are not going to, and I'm guessing probably about 3/4 of them are registered voters. We're not going to call 3.5 or 4 million people and ask them who they're going to vote for. First, actually, we'd have to ask them if they're going to vote and then who they would vote for. There's a lot of reasons why we wouldn't do that. One, of course, is money. It'd be very expensive to call that many people. Labor, equipment, and all sorts. If you had to mail them surveys or whatever, that'd be expensive as well. And of course, time. You don't have the time to get a hold of all those people. So time and money, of course, are are usually the big determining factors in a lot of things. The next ones are kind of a little bit more obscure. The third reason that I'm going to discuss is changes over time. Now, this one you might be wondering, well, how is that different from just time itself? Well, because the goal of these types of things is to take a snapshot. Because technically what we're doing is we're not actually trying to, the information we're gathering isn't really about who you're going to vote for when the election comes around. It's who you would vote for today when we're asking you about it. That might change. Well, if you're trying to survey everybody in this population, all the registered voters, it's going to take you a long time. And during the course of that time, things might happen. There might be a scandal that comes out on the news, or maybe one of the candidates give a speech that's just right on the money and gets a lot of people fired up to vote for him. So if it takes you several days to do this, well, there's a good chance that some of those first people that you surveyed several days ago might change their mind. They said they were going to vote for candidate A last week, but now something happened over the weekend. Now they're going to vote for candidate B. So you're not really gathering that information under the same conditions. The conditions have changed. So when we talk about changes over time, that's what we're talking about. My pen's been acting up all day today, so hopefully we get through her. I say defining the population. It may be difficult to define the population. Now, like I said, in this case, our population really isn't all registered voters. It's those who will vote in that election. Well, they might not know if they're going to vote for sure or not. Or again, some of those changes over time. Right now, they don't plan on voting, but something could happen that gets them wound up and they decide they're going to vote. Or maybe they do plan on voting, but election day comes and their car won't start, or something happens. So there's defining the population might be a little fuzzy, so getting a hold of everybody in the population is a little tricky. We'll get to that. Yeah. Now, this next one refers to populations that not really people, but of things. Destructive testing. One of the things that statistics is used for is for quality control. Now, manufacturing, maybe you produce parts that have to hold a certain amount of force. So what you do is you take one of the parts and you test it. You put it in a machine. It's going to put force on it, and it's going to keep putting force on it until it crushes it, until it breaks, basically. Then you look at that amount of force, and you compare it to the amount of force that it needs to be able to hold. And if that force is enough larger, you know, hey, it's pretty safe that would have held because it held way more force than what it needs to. Well, obviously you can't test every piece because testing them breaks it. And so if you tested every piece, there wouldn't be any pieces to use. So you test a certain number of them and you assume that if those are good enough, that the rest of them are hopefully good enough as well. And there are other lesser common reasons or lesser prominent reasons why you would not want to contact the whole population. You mentioned the word census. A census actually is an attempt to gather information from every, now I'm going to say element. An element could be a person or a thing. An element is just each item in a population. The United States Census comes up every 10 years. It'll be coming up here in 2020. The United States has never done an actual complete census. There's always been at least one person that refuses to give their information. There's just no way around it. That's one of the reasons why the way that you can't gather from a whole population is because of that. Some people just won't do it. But they do make that attempt to gather information from every person in the United States. Technically, it is actually a federal crime not to respond to the census. A parameter is information gathered through that census. In other words, it describes the population. Now, there are a lot of types of parameters for a population. There are demographic parameters, like that there's 5 point whatever million people in the state of Wisconsin, or however many voters there are, age ranges, registered, those are things that describe the population. They're demographics. Those are not the parameters we're concerned with. We're concerned with parameters of interest. And a parameter of interest is something that's relative or relevant, I should say, to what we want to learn. A parameter might be 60% of all registered voters, or all voters who are going to vote in the next election are going to vote for candidate A. That would be a parameter. Now, it may not be a precise parameter, but it is a statement describing the whole population, and it is relevant to what we're trying to learn. So since we spent the last 15 minutes or so talking about how we can't gather information from the whole population, so what do we do? Well, we take something called a sample. For those reasons listed above, we take a sample, which is a smaller group. Technical term would be a smaller set selected from the population. In some instances, yes, but that's a special case. So, things about our sample. We take this sample, which is a smaller group, and we try to gather information about that. That is a survey. So a survey is gathering information from a sample. Now, what we've kind of discussed so far is surveys of the form of asking you questions and getting answers. There is that type of a survey, which is called an observational survey. An observational survey or observational study, you are just gathering information. You're asking questions, or you sit back and watch and see what somebody does, and you record that information. There is also an experimental study or experimental survey. And in experimental, you still gather information, but you have to introduce some conditions. That's like that quality control thing. You actually put a force on that part and see if it breaks. That's an experimental survey or experimental study. Medical research, those are experimental studies because you give some sort of a treatment and you see what happens. So that's the survey, is that gathering of information from that sample. And then a statistic is information that describes the sample. So the whole point of the field of study called statistics is to figure out how to gather statistics that closely approximate our population parameters. Because it would be too costly and time consuming to actually gather the information from the whole population, we gather it from that smaller sample. But it's no good to us unless that information from the sample is very, very close to the exact same information as in the whole population. If we go to a young Republicans meeting and gather information there, well, a good share of them are probably going to vote for the Republican candidate. That result is not going to closely represent the whole state. So what it comes down to is something called a representative sample. And a representative sample is just that. It is a sample in which the statistics that describe the sample are very, very close to the parameters that would describe the whole population. Now, the thing is, we don't know what the parameters are, so we don't know whether the sample statistics are close to those parameters. If we knew the parameters, there'd be no reason to take a sample. We'd already know what we were trying to learn. So what we have to do in statistics is take measures to be careful and hope that if we're careful enough, the sample we get will be representative. But that's the kind of that frustrating part of statistics is we'll never truly know whether it really was representative or not. It's a generalization, yeah, but we're trying to do it, we're trying to follow rules and procedures that give it a higher chance of being representative, basically. And you might say, well, we could test to see who actually wins the election and take those results. Well, remember, it's conditions. If I take my sample today and the election is tomorrow, there may have been something that happens tonight that changes some people's votes. So it's not necessarily the same condition. So I'm still not really confirming my representative sample. So it's a tough thing to do. So ways to confirm that representative sample. There are two big factors we consider. One is sample size. In general, bigger is better, to a point. In many cases, we say there's a minimum of 30 to be a good sample. By the way, we let little n equal the size of a sample. So the notation here would be that n has to be greater than or equal to 30. Now, there are exceptions to that. If we have certain inside information about the population, then we can take smaller samples. One of the big ones is you have to know that it's approximately normally distributed, which we'll talk about that a little bit later. But in general, you wanted that sample to be bigger than 30. Now, bigger yet, of course, would be better because the more you take, the better the chances are that, so you happen to get some radical viewpoints on one end. If you have a big sample, there's a good chance you have radical viewpoints on the other end, and they'll balance each other out. Like testing, if you're testing those parts, there's a chance you get some really weak parts, but a chance you get some really strong parts, and they cancel each other out and give you an average that is pretty reliable. If you're taking a small sample, there's always that chance that you just happen to choose a sample with weak parts in it. And so you might get a low value, or you might just choose a sample randomly that has stronger parts in it. So the bigger the sample is, the more likely those extreme values are to balance out in the end. Now, I said to a limit. There comes a point where if the sample is more than a certain percentage of the population, it's just too big. The randomness is gone, and so you just will do the whole population. Yes. Yeah, you're trying to get a big enough sample so you can get all the different nuances of the population. And again, cancel out the chances of just randomly selecting a sample that leans one direction or another. Yes, yes. Like in a medical study, if I'm testing a new medication, if I only select 5 people to test that medication, well, there's a chance some patients get better even without treatment. So there's a chance that the 5 people I chose would have got better even without that treatment. So, I mean, it's not likely, but there is a chance. Yeah. Yeah. But if I have a sample of 50 people, well, it's very, 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 very unlikely that all 50 of them would have got better on their own without the medication. So that bigger sample, it's just less likely to choose extremes. Then the other thing is the selection process. And so we're going to talk about our selection right now. Selection must be random. Let's take a look at how that works. What does random mean? Well, there's actually 2 phrases I'm going to define for random. The first one is random itself. Random simply means every item in the population has an equal chance of being in the sample. So every item in the population has an equal chance of being selected for that sample. Now that sounds pretty good, but statistically speaking, that's not quite good enough. For many of our simpler processes, random is okay. But as you get into some more of our more complex processes, like hypothesis testing, which we're not going to get into in this course, but that would be the process you actually have to go through for drug testing and stuff like that. A random sample is just not good enough. We require something a little bit stronger called a simple random sample. In a simple random sample, remember we said n is the size of the sample. Once we've chosen that size, all possible samples of size little n have an equal chance of being selected. We might be wondering, well, how is that any different? Well, there is an important difference between them. And let's give you some examples to kind of point this out. One type of sampling that gets done is something called systematic sampling. Systematic sampling often takes place in manufacturing, where we have that quality control testing. Let's say we want to test 1 out of 100 parts. So 1 of every 100 parts. Well, what we could do is just, list off how many parts we're going to produce that day and randomly select numbers. Well, that's kind of difficult to do because we don't necessarily know how many we're going to even produce. But what we could do is this. We're going to randomly select a number from 1 to 100. So let's say, for example, we choose the number 38. So that means for the first 100 parts produced, we're going to take part number 38, we're going to test it. In the next 100 parts produced, we're going to take part number 138, and then 238, and 338, and so on. So for every 100 parts produced, we're going to take the 38th part out of that lot of 100. Well, this is random, because every part has a 1 out of 100 chance of being selected. Every part has the same chance of being selected to be in that sample of parts tested. It is not simple random. Why is it not simple random? Remember, simple random is every sample of that size. Well, there's no chance that 2 parts out of the first 100 are going to get chosen for that sample. It's just not part of the system. So it's not simple random. So this is acceptable for some of the lesser processes, but not for the more complex processes. Another type of sampling that's popular is cluster sampling. And what we do in cluster sampling is we divide the population into groups. And then we randomly select whole groups to test. Why would you do this? Well, let's say that you are a communications company and you want to test the signal strength at different houses throughout the city. If you just randomly selected houses throughout the city, you're going to be sending people out there to test. You might have one house here, one here, one here, running all over the place to test houses. Which again comes down to that time and money and resource type thing. So what would be more efficient is to say, we're going to divide the whole city up into city blocks, and we're randomly going to select whole city blocks. So we'll send somebody out to this block here and test every house on that block. And we'll send somebody out to this block here and test every house. And maybe this block here, and we're going to test every house. So they can go there, park, and get a large number of data, large amount of data at one time. That is random because every house has an equal chance of being selected. But it is not, again, simple random. Because there's no chance that you're going to get a sample where there's one house from every block. Each sample that you get is going to contain every house from the block selected, not just some of them. So it's not possible to take every possible sample. Now again, for many things that you would do, that is acceptable, but not for the more advanced process. There's also something called stratified sampling. In stratified sampling, for example, well, what you're going to do here is you're going to divide the population into groups. And you're going to select some from each group. Now I'm oversimplifying that a little bit. You would select what's called a proportional amount from each group, but we don't need to get into those details. For example, let's say that you want to gather information about health benefits for the company you work for. Well, you have people in management, you have people in the office, and you have people in production. You don't want to just, choose names out of a hat and you might accidentally get a sample where everybody's in production. Well, you want everybody else to be represented as well. So let's say that 80%, wrong colors here. Let's say that 80% of the people, of your employees are in production, 10% are office, and 10% are management. So what you want to do is you will divide your employees up into those groups, and you'll take, for every one person of management you sample, you'll take one person from the office staff and 8 people from production. So you get the right ratio of people from each group into that sample. Now, this is definitely random because everybody has an equal chance, but again, it's not simple random. Because it is not possible to choose a sample where everybody's in production. It's not even possible to choose a sample where the proportions were different. So what is a simple random sample? A simple random sample can be tough to do because a simple random sample, to be a simple random sample, you must identify everybody in the population. The best example of a simple random sample would be to give everybody a number or write down their name or whatever, put them in a hat, and draw them out of a hat. Now, of course, there are computer programs to do this random selection or whatever. But the problem there is it does require you have to identify every item in the population. We can't take and assign every voter that's going to vote in the next election a number, put them in a hat and draw them out to make our sample, because we don't know if they're going to vote in the next election or not. So a simple random sample is almost impossible to purely take in many cases. Now, like for the school here, if I wanted to take a simple random sample of all students that are currently enrolled, well, that's easy because I can pull that data out of the computer system. I mean, that's a small enough group that I can get that whole population and I can draw a sample out of that. But in many cases, the whole population is fuzzy enough that it's difficult to do. There's also something called a convenience sample. And I'm going to say this right up front. As Charles Barkley would say, they're terrible. They're not reliable at all, but they are done because they are easy. The term convenient is where the name comes from. Convenience sample is what most of the samples you see on the news are. If you see, that 87% of people surveyed responded in favor or responded against this. Well, why is it that those are convenient samples? Well, because they have an issue called self-selection, for one. Well, if I call you and you answer the phone and I say, hey, I'm doing a survey about, you have a choice to either answer or hang up on me, right? Well, self-selected samples they're just one type of convenience sample, but if I identify, let's say I call up and say, hey, I am from the Wisconsin Democratic Party, I'm doing a survey, and well, if you're Republican, you've just hung up on me most likely because you don't want to hear from the Wisconsin Democratic Party. And the other way around, So chances are, by identifying myself for what group I'm from, I am going to get a sample that's more likely to be in favor of the topics that I'm asking about. So, by you being able to opt out, it makes it so that it skews the data. I actually did a study when I was in college. I worked for the Statistical Research Center, and one of the experiments we did was we sent out 500 envelopes. We got permission from the Wisconsin and Republican and Democratic parties, and we actually got envelopes from them. We sent out identical surveys. All they had was a little symbol in the bottom corner so we knew which envelope they went out in. And we sent out 500 each. One was envelopes from the Wisconsin Republican Party. The other was envelopes Wisconsin Democratic Party. Same survey. First of all, we only got back about 130 from each of them. Very low response. But guess what type of answers we had on the political surveys that went out in the envelopes from the Wisconsin Republican Party? Very conservative answers. Because if you're a Democrat and you get an envelope from the Wisconsin Republican Party, chances are it doesn't even make it in the House. I know I wouldn't open it. It would. Yeah, it goes in the trash. So by having that marked on the envelope, you're interfering with the results of the study. Another form of convenient sample is just go ask your friends. Well, that's not very reliable at all because your friends most likely have some views similar to yours. Or you might go to a single place. Let's say I want to learn about how much students spend on books. So I'm going to go out in the hallway outside my classroom at noon tomorrow and ask the first 20 students walking by. Well, that's convenient because I'm just going out my door and the first people go by. Well, students from other campuses have no chance of being in that survey. Students that only have night classes have no chance of being there. Students who only take online classes have no chance of being in that sample. Only students that happen to be at Rice Lake campus and walking by my door at noon tomorrow have a chance of being in that survey, in that sample. So that's a convenient sample. It's easy for me to do, but it's not very representative. Or the chances of it being representative are pretty poor. And there's always a chance that a poorly taken sample could be dead on to the population, but the chances are quite a bit lower. So we've done all those things correctly. It's time to start gathering information. Well, when we are dealing with whether it is an observational study or an experimental study, we are going to ask a question. That question might be, who are you going to vote for? Or the question might be, what's going to happen if I do this, in the experimental side? Or if I give you this medication, do your symptoms, reduce or get worse? There's some sort of question we're asking. The random variable is the answer to that question. We have two main types of random variables. There's categorical, or sometimes called qualitative. Or we have numerical or quantitative. Categorical, qualitative, a category or a quality of an object are kind of the same thing. If you ask a qualitative question, the answer is going to put you into a category. An example of this might be favorite color. Well, your answer puts you in the category of people that like that color, because hopefully there's other people that like that color too. Any yes or no question is categorical, because it puts you either in the yes category or the no category, depending on what you're asking. Of course, then quantitative, you're measuring a quantity, or the result is a number. So the answer is a number. How many kids do you have? How many cars do you own? How tall are you? How old are you? How long does it take to do this? How much does this object weigh? How much force does this object take before it breaks? Those are numerical or quantitative. Now, there are two different types of numerical variable. There is discrete. Discrete means it can be counted. And there is continuous. Continuous is something that is measured. Now, there are some obvious discrete ones, like number of children. How many kids do you have? Or number of cars you own, or number of classes you're taking. Those are things that are counted. There are some obvious continuous ones. Height, weight, length, whatever. Then there are some that are kind of in that gray area. Money, time. Money, if we stick strictly to the sense of a monetary system where there is a smallest unit, and of course in our monetary system that's a penny, it can be continuous. Now in the electronic world we know that computers calculate money down to very small decimals of a penny, but it still cuts it off somewhere. Time, now if you're counting time in days, that's probably more discrete, but time for the most part is considered to be continuous. Another definition of continuous is no matter how close two numbers are, it's possible to find one in between them. Well, that's why time goes into continuous, because no matter how close two times are, it's possible to find a time that's in between them if you go down to enough decimal places. Okay, that brings us to our break time, so let's go ahead and take our break, and we will come back and start talking about organizing data. So at 6:20, let's come back at 6:30. So we have all this vocabulary. What are we going to do with it? Well, after we've done our survey or our experiment, we start out with a lot of raw data. And raw data is just that. It's a list of answers to that question. So let's do the example of favorite color. This is a categorical. And let's say our choices are going to be red, blue, and green. So I'm just going to do R for red, B for blue, G for green. So we're going to list out the responses. Let's see what I have there. 1, 2, 3, 4, 5, 12, 13. So what I have here is 30 responses. Now, you don't necessarily have to list those out in your notes. But if I were to ask you, what is the most common response? Well, you can stare at this and it isn't necessarily going to come to you, right? The human brain can only really comprehend between 7 and 13 items at the same time. So when you look at this, you're not going to see all of it at once. So if you happen to look here, you're most likely going to say, what color is the most popular? Blue. There's a lot of blues there. If you happen to look right in here, you're going to most likely say green. Over here, red. So it all depends on what draws your focus. You really can't take them all in at the same time. So one of the things we're going to do to organize them is called a frequency table. And a frequency frequency table is almost always the first level of organization. And a frequency table is just 2 columns, but we're going to add a third. The frequency table, the first column is the item. In this case, it's color. You know what? I should take the blue out of it just to avoid the bias. So color, and we're just going to list them: red, blue, and green. Now I'm going to ask you, does it really matter what order I list those colors in? No. There is no logical order to put them in. I can list them in whatever order I want to. That's going to be important in a little bit when we discuss some other things. Now the second column is frequency. Now notice I left it over there with a little bit of a space because I'm going to add a third column. And this third column I'm going to call the tally column. This would not be included in the final table. When I present this to someone, that column wouldn't be there. It's a working column that helps me make the table. So what I'm going to do is I'm going to look here. I've got red, blue, blue, red. Red, blue, blue, red. I'm just putting the tallies into my column. Green, blue, red, green. Green, blue, red, green. Green, red, green, blue. Green, red, green, blue. Now, would anybody have guessed that at this point we'd be dead even in all of them? Not really by looking at them, would you? Blue, red, red. So blue, red, red. Blue, green, blue, blue. Blue, green, blue, blue. Red, green, green, blue. Red, green, green, blue. Green, green, red, red. Green, green, red, red. Again, not many of you would have guessed we were dead even at this point. Green, red, blue. Green, red, blue. All of them had exactly 10 responses. Anybody would have looked at that data and guessed that they were all the same? Most likely not, no. So that is the first step in organizing data, is to get it into a frequency table. Well, that was categorical data. Numerical data again depends on whether it is discrete or continuous. If it's discrete data, like number of cars owned, we might just make a table like this: 0, 1, 2, 3, 4. And let's just say that of the people we surveyed, 4 was the most number of cars that anybody owned. And we're taking that raw data. Right now, just like we had that list of colors, we would have a list of numbers: 0, 1, 4, 1, 1, 2. I'm not going to make that list right now. Let's just say that of the people surveyed, 2 responded that they had 0 cars. 34 responded that they had 1 car. 18 responded 2 cars. 7 responded that they had 3 cars. And actually, let's check that. Let's say 5 responded they had 3 cars, and 1 responded they had 4 cars. So there is our table. Now again, if I just had a list of numbers, 1, 1, 0, 1, 2, 1, 1, 1, it'd be tough. You probably look at it and pretty obviously see that 1 was the most common, but it's a lot easier to see once it's organized like this. If it were continuous, that's usually a little more difficult to list. For discrete data like this, especially when there's a relatively small number of possible numbers for response, there's going to be multiple responses of each number. For continuous data where it's something measured, it's very unlikely to even get 2 items that are exactly the same. For example, let's say we're going to do height. Well, height, of course, can be measured down to a fraction of an inch. So let's say we're going to measure people down to the 10th of an inch. So you have someone who is 68.2 inches. The next person is 65.9, 71.3, 73.2, 67.4, 69.3, 70.8. I could make a pretty big list of numbers here, and because I'm going down to a 10th of an inch, I might only get a couple of them that are even the same. So I'm not going to list every value. So what I'm going to do here, now obviously that's not a complete set of data, but what I'm going to do here is I'm going to group it. Now the grouping here is kind of the difficult part, but let's just do, height is going to be the groups that we have here in frequency. The grouping, there's a couple of conditions that you have to have. They have to include, of course, the whole range of the data. That's pretty obvious. But the groups must be the exact same size. You can't have one group go from 60 to 62.9, then from 63 to 70. I mean, they have to be the same size. So let's say that the shortest person we had in the group, the smallest number is 62 inches, and the largest was 76 inches. That's just for, let's say 76.9 to make it simpler on us. Coming up with the number of groups you want to use and how big each group should be, it is kind of difficult. There's not an exact science. A lot of textbooks try to come up with, you take, n, which is the number of items in the list, you take the square root, that's how many groups you should have, or it's really not quite that simple. It's one of those things that you just have to kind of get a feel for the data. So we're looking at this. Let's just make each group 3 units long. So what I'm going to do is this. This is going to go from 62 to 64.9. Then 65 to 67.9. Notice those are exactly the same size. One of the other conditions that we have to have, not only do they have to be the same size, but there can't be any gaps. What that means is it can't be possible for a data value to fit in between classes. And here that is not possible. Since we're only going to the 10th of an inch, it can't fit between 64.9 and 65. Then it might be 68 to 70.9. And 71 to, or 73.9. And 74 to 76.9. Now, obviously, this worked out perfect. We started out with our smallest number. We ended on our largest number. That's not always going to be the case, that you can't get them always to work out perfect. So if this one has to be a little smaller than your smallest number, and this one has to be a little larger than your largest number, try to space them out so it's even. So you go past the same amount on each end. Like I said, this part is the most difficult part of coming up with classes. For this class, what would normally happen is I would give you the first one, and then you would have to make the rest of them from there. So if the first one is 62 to 64.9, well, you know the next one starts at 65. And the difference from here to here is 3 units. So you have to add 3 here to get that next one. You add 3 here, and so on. And then, of course, you would go through the data. You'd probably do a tally column just like we did before. And you'd come up maybe 5 people in this survey or this study were between 62 and 64.9. Maybe we had 12 from 65 to 67.9, 23 from 68 to 70.9, 18 from 71 to 73.9, and 4 from 74 to 76.9. We've got our data organized. So now you can very quickly, again, look at this and say, hey, the most common height range is right there. Once we have grouped data or organized data into a table, the next step would be to graph it, to organize it graphically. If we have categorical data, let's look at that favorite color again. Now I'm going to change the numbers here just because it's really boring to graph 10, 10, 10, right? So let's say we have red, blue, and green. And let's say we take a larger sample, we add some to that, and we get that red is 18, blue is 13, and green is 19. One of the graphs we could create would be a bar graph. There are two varieties of a bar graph. Statistically, the most common is vertical. In a vertical bar graph, you put the categories across the bottom: red, blue, green. And up the side, you label the frequencies. Now, what's the largest frequency I have to make it to here? 19. So I have to make sure I get up to at least 19. So I'm going to label by fives, 5, 10, 15, 20. And now I'm going to put my bars in there. So red has to go up to 18. Looks like that. Blue goes up to 13. Green has to go up to 19. So we can look at this graph and very quickly see the smallest, of course. Which one was chosen the least? Blue. And the largest, which one was chosen the most? Green. Now that's a little, they're kind of close. That one's a little trickier. The other thing we can do very quickly is we can compare. Which one was chosen the most often, red or blue? Well, you just look, red has a taller bar, it's the most often. So more often than blue. The other option is we could have a horizontal bar graph. And all that would be is the colors are on the side and the numbers go across the bottom. And we would draw the bars in. I'm not going to draw those in just because I don't want to bother. Notice I didn't necessarily use the same scale. I had more space there, so I could number by 2s instead of 5s. So you can see the strength of a graph, of a bar graph, especially as you can very quickly see which one's largest, which one's smallest, and you can compare any two of them. Now there's only 3 here, so there's not a lot to compare. But another type of graph that is often used with categorical data is a pie graph. Sometimes called a pie chart. For a pie chart, we have to convert this into something called relative frequency. To find relative frequency, the first thing we have to do is get the total frequency. If we add those all up, it adds up to 50. Then we're going to use that total to find the percent frequency. Now, relative frequency and percent frequency are slightly different, but they're really not. If I take 18 divided by 50, that's 0.36. 0.36 would be the relative frequency. The percent frequency is 36%. Again, we take the frequency for blue divided by the total. 13 divided by 50 is 0.26. So that's 26%. 19 divided by 50 is 0.38. That's 38%. Total frequency. Now, if this were 30 years ago, we would take those percents and we would find 36% of 360, because there's 360 degrees in a circle, and we would then take a protractor and measure out that many degrees to make our graph, our table, or our circle. But now there's computer programs to do that. If we want it that exact, we'll use a computer program. So what we're going to look at basically is half a circle is what percent? 50%. Quarter circle would be 25%. Of course, if we cut that into an eighth, that would be 12.5, right? We keep cutting it down smaller and smaller. Well, here we have blue is 26%. That's really close to a quarter circle. So we're going to make it just a touch larger. That's blue. The other two are pretty close to the same, with the green being just slightly larger. Well, 25 plus 12.5 would be 37.5. So if I look at this, if I divide this here and there, it's just a little bit bigger than that quarter plus another eighth. So I'm just going to put it right in there. That would be green. And this is the red. And obviously those gray lines would be out of there. For what we're doing, that's close enough. We don't need to be exact. But the key is to find those percents and graph those percents. Now, I did something on purpose here because I want to point out some things. Graphs can often be used to deceive. I purposely wrote all these in blue ink because even though you are reading the words red, green, and blue, your mind is seeing blue. That is something that there's a whole branch of statistics that blends into psychology, the psychology of statistics, that is used to take legitimate statistics and try to elicit a response. Because statistics don't necessarily have a set conclusion. You look at these numbers and this is your set conclusion. You look at the numbers and you can interpret them in different ways. Well, there's things that can be done that can influence how you interpret them. By making all these blue ink, you might look at it and see, well, the biggest one is this one here, but it's in blue ink, so your mind associates it with blue. So when you do advertising and stuff like that for companies, they do a lot of those things. Now, the other thing that gets done with like bar graphs, let's say I'm comparing companies A, B, and C. We'll get to that. So you can see my numbering here. I've got this little hash mark here. You can see my numbering starts at 200 and goes to 205. It looks like A is like 3 or 4 times B, doesn't it? But realistically, B is like just over 200. C is not quite 201, and A is between 204 and 205. This hash mark here means I cut out part of that axis. And I'm focusing on the differences. If I did this with that full axis there, well, I might do 50, 100, 150, 200. They're really close. And now there's an advantage to this graph here. It's easier to see the differences, but there's also that psychological effect. If I'm looking at this one here, I'm saying, wow, A is way bigger than the others. If I'm not careful and force myself to look at this and put the numbers into it, I might get the wrong impression. Here, it's tough to see what the actual values are, but I can tell that they are pretty close together. Now, I actually did something intentionally here, too. I made some of the bars narrower than others. If those bars are not the same thickness, again, psychologically, your mind looks at this thicker bar and says, that's bigger. Even if they're the exact same height, your mind's going to say, that's bigger. That gets done a lot. There are a lot of things that are done in statistics to try to deceive. Using real numbers, legitimate numbers, trying to trick your mind into perceiving them a little bit differently than what reality is. Now, the other thing you'll notice, even with this one where it's focused in, well, is that 204.4, 204.5? I don't get the exact number, do I? Graphs give us an approximate number. If I want an exact number, that's where I go back to a table. So these are categorical data. Now, remember, I made a big deal about there is no real logical order to put red, green, or blue. I could put them in any order here and it would still make sense. Notice I left space between the bars here. If I'm dealing with numerical data, let's go back to those heights again. Now, I'm not going to bother to go back and look at my actual frequencies that I had before. I'm just going to put in new ones here. Something like that. When I go to make a graph of this, the equivalent of a bar graph is something called a histogram. And a histogram is just a bar graph for numerical data. A histogram is always done vertical. And then across the bottom, instead of categories, we have these number ranges. So 62 to 64.9, 65 to 67.9, and so on. Now, some books allow you to just put in like the midpoint, like 63.5 or whatever. Other books just have you labeled, this is 62, this is 65, and so on. There are other ways to make it shorter so you don't have to put the full range in. I'm a little bit of a purist, so I usually do put the full range down here. And of course, up the sides, once again, we have the frequencies. We have to make sure we get up to at least the highest frequency. Now, when I put these bars in, 62 to 64.9 goes up to 5. Then 12, 23, 7, 4. Do you notice anything different about the way I drew those bars? Yeah, they're touching. Why do they touch? Well, because there's a logical order these go in. 65 to 67.9 comes after 62.64 to 64.9. Comes before 68 to 70.9. They must go in that order. That's the logical order they go in. Also, one flows into the other. I mean, 64.9 kind of borders right on the 65. So we do that. That's part of being honest with the psychology. When your mind sees that, your mind tends to bring that conclusion in that those do blend together. And it's true. So that's why we draw it that way. Now, there's a whole branch of statistical ethics and statistical psychology that we just don't have time to get into. There's some little things that I showed you about ethics, how you could mislead with the data. It's a huge, huge topic of like I said, we just can't get into it here. I mean, that could be a whole class in itself. I am very big on ethical use of statistics because I've been paid to twist statistics. I have seen statistics just twisted to give ridiculous answers. Mark Twain once was quoted as saying, there are lies, there are damn lies, and then there are statistics. So obviously you can see his opinion of them. I mean, you can give me a set of data and two totally opposite conclusions, and I can find a way to make that set of data prove both of them true, just analyzing it differently. So there's a lot of ethics involved here that we were not going to discuss. So anyway, those are those two main types of data. Now there's another type of graph that we're going to show, and it's called a time series graph. Everything that we've done so far has been just kind of a snapshot at a single moment in time. This is what the values or the outcomes were. A time series graph goes over a period of time. It measures one thing, and it measures it over and over again. For example, we might look at WITC tuition per credit. So cost per credit. We might have 2000, 2005, 2010, and 2015. That's our year, and this is our cost per credit. In 2000, it was about $92 per credit. In 2005, it had jumped to $134 per credit. 2010, it had jumped to $148 per credit. 2015, it sank back down to about $144. To display time series data, we use something called a line graph. On a line graph, time always goes across the bottom. What represents time here? My years. 2000, 2005, 2010, 2015. Now, I'm going to do something I've told you not to do. I should start out 0, 20, 40, 60, 80, and so on. But in order to make this look a little nicer, I'm going to start out at 90, 100, 110, 120, 130, 140, 150. I'm going to put my dots on there. In 2000, it was 92. 2005, 134. Oops, back there. 2010, 148. 2015, 146. There's a couple of things we can see from this line graph. One, we can see where it's increasing. From 2000 to 2005, it was increasing. 2005 to 2010, it was increasing. Two, we can very quickly see where it's decreasing. From 2010 to 2015, it decreased a little bit. We can tell where it was moving the fastest. The line is the steepest here between 2000 and 2005. That's where it was growing or increasing the fastest. Now again, the graphs are good for doing those comparisons and finding those trends. If we wanted the exact numbers, I'm not going to get $134 by tracing this back. It's going to be a little blurry. I have to go to the table to get those exact numbers. Okay, so that's representing these graphically. And there are other graphs that we haven't discussed that I'm just going to assume that you guys are familiar with them or can pick them up out of the notes. Our next step now is to summarize data numerically. To summarize data numerically, we need to talk a little bit about data distribution. So let's take, for example, let's say we're going to talk about a quiz that I gave in one of my classes last week. So what we do is we make a number line with the range of our data on it. Let's say that the lowest score on the quiz was 12. And the highest score was 25. That was the full score. So I make a number line with the range of my data. And so now I look through my quizzes. Let's say my first quiz was a 21. Next one was an 18. Next one was a 20. Then a 22. Then a 13. Then a 17. Another 18. A 24. A 16. A 19. Another 20. Another 19. And as I keep scoring those quizzes, I add their scores to this plot. And as if there's multiple in the same score, I just put the dots up above them. I stack them up. And what happens over time is you see that the center of this gets taller and it starts to form a very definite shape. And if I trace a line through the top of those points, I get a shape that looks like that. That is what a lot of us have heard referred to as the bell curve. Its technical name, we've mentioned it earlier tonight, is called the normal distribution. Because in nature, that is the shape that data normally takes. If I were to take 1,000 people, measure their height, and plot their height on a number line like this with a dot plot like that, I would get a bell-shaped curve, most likely. Now, there are two things that can be used to describe that curve. The first thing is the center of that curve. I'm just going to go down here and draw another example. So let's take this curve right here. If I were to describe that curve, I'd find its center right there. Looks like it's at about 21. So I'd say the center of that curve is at about 21. Well, I could take another curve. How would I describe the difference between those two curves? Yeah, the center of the brown curve looks like it's at about 17. They have a different center. How would I compare this purple curve? Let me draw that a little bit better. To the black one. Well, their center's at the same spot, isn't it? Yeah, the centers are the same, but they're not the same curve, are they? How would I describe the difference? Tighter, narrower? What we're talking about there is spread. Oops. Helps if I put my R in there. Spread, sometimes referred to as dispersion. How spread out are the numbers? Assuming that each of these sets had the same number of scores in them, we could say that the purple set, the scores are probably closer together. They're less spread out. So we're going to describe these by talking about their center and spread. And it gives us that picture of their distribution. Now we're going to assume our distributions are symmetrical. They're bell-shaped. But not all distributions are symmetrical. They can be skewed. Skewed means they're stretched out in one direction or another. This one here is skewed to the left because it is stretched out on the left side. This here is skewed right because it's stretched out on the right end. I did a horrible job of drawing those, but hopefully you get the picture. So let's start out by talking about our measures of center. Now, in statistics, there are dozens, if not more, measures of center. But there are really only a few that are commonly used. So we're going to talk about 3 or 4 of them. The first one we're going to talk about is the mean. Mean is what most of us have been taught since about 3rd or 4th grade, is the average. So let's take a set of numbers here. I'm going to write them down here. And let's say we're going to have 17, 5, 9, 11, 10, and let's go 14. So those are 6 numbers. Let's find their mean. Well, how do we find an average? We add them up. The symbol for that is that right there. That's called the summation symbol. X stands for each of the numbers, and then we add them up is what that means, and we divide by how many are there. Remember, n is the number of items in the list. So we've got 17 plus 5 is 22, plus 9 is 31, plus 11 is 42, plus 10 is 52, plus 14 is 66, and we're going to divide by 6 because there's 6 of them in the list. That gives us a mean of 11. That's one that we're all usually comfortable with because we've done averages for years. Well, the next one is the median. The median is the middle number. To do the median, it takes a couple steps. Step 1, put them in order. So we have to put them in order from smallest to largest. So let's do that right here. So the smallest number would be 5, then 9, 10, 11, 14, and 17. Step 2, find the position of the median. How do we do that? Well, we take n times 1/2 or 0.5. The median finds the middle. It cuts the data into 2 halves. N for this set of data is 6 times 0.5 or 1/2 is 3. Since this came out to be a whole number, that means the median is between that number, the 3rd one, and the next one, which would be the 4th one. So 10 is the 3rd number, 11 is the 4th number. So between them, we would do 10 plus 11 and divide by 2. Now, when you do this on your calculator, do 10 plus 11, make sure you hit equals first before you hit divided by 2. Because if you just do 10 plus 11 divided by 2, it's going to try to tell you that this is 15.5. That's not true. We know it has to be between them, which is 10.5. Now, in that case, we said that this worked out this way because this was a whole number. What if it wasn't a whole number? You know, this was with n equals 6. It came out that way. What if we had something like n equals 13? That'd be a different set of numbers, not this one here. Well, n equals 13, we would do 13 times 0.5 gives us 6.5. Since that is a decimal, we round up. So the 7th number in the list would be the median. So we don't have a new list of numbers with 13 items in it, but we would find from smallest to largest the 7th number, that would be the median. That's always, yes. Go up to the next one. If it's a whole number, it's always between that one and the next one up. Our third measure of center is the mode. The mode is the number that occurs most often. Now, it is often possible to find a mode in numerical data. For the data set I have here, there is no mode because there's no number that appears more than once. Now, depending on what textbook you're looking at, some textbooks say there's either one mode or there is no mode. Some say it can be something called bimodal. There can be two different numbers that are the most often. Others say it depends on the size of the set. For our purposes in this class, there's one or none. And this data set, there is no number that's repeated more than once, so there's obviously no mode here. There is a fourth measure of center that I'm going to give here called the mid-range. The mid-range is found by taking the smallest number and the largest number. The minimum is the word for the smallest number. Max or maximum is the word for the largest number. We add them together and divide by 2. So for this data set here, the smallest was 5, the largest was 17. So we do 5 plus 17. Now again, make sure you hit equals before you divide by 2. So 5 plus 17 is 22, divided by 2 is 11. Now notice the measures of center that we had there were all pretty close. We had a mean of 11. We had a median of 10.5. We didn't have a mode. We had a mid-range of 11. If this data was perfectly normal, perfectly normally distributed is the technical term, all of those would be equal. The mean would equal the median, would equal the mode, would equal whatever other measures of center we decided to use. Now we talked about skewed. If the data is skewed to the left, well, the mode is the number that's the most often, so that's the highest point on the curve. The median is in the middle. That would be slightly to the left of the mode. Remember, the median has half the numbers on each side of it. The mean is the average. That would usually be a little bit further to the left in the direction of the skew. We had numbers that were skewed right, or distribution that was skewed right. Obviously, the opposite would happen. Our mode is still the tallest spot of the curve. The median would be slightly to the right. And the mean would be a little bit further to the right. So if you have the mean, median, and mode of a set of numbers, you can actually tell how it's skewed just by looking at how different they are, what the direction that the mean varies from the others. One of the first ways of testing to see if it's approximately normally distributed is to see how close they are. If those numbers are really close to being the same, well, then it is approximately normally distributed. What we have here, those are really close to being the same. We could say that this data set is approximately normal. Okay, it is time for our second break. So let's take our second break. It's 7:20, so let's roll. So we talked about measures of center. Our next step is to talk about measures of spread. So spread. Now, just like measures of center, there are a lot of measures of spread. We are going to talk about a couple of them now, and if there's time next week, we might talk about some others. But the main ones that we need to know, first of all, is the range. The range is simply the difference between the largest and the smallest. So let's take a set of numbers here. I'm going to write them down here again. Let's do 11, 7, 18, 9, and 10. So there's a set of numbers. The largest number in that list is 18. That's the max. The smallest number in that list is the 7. That's the min. 18 minus 7 gives us a range of 11. Now, range is very quick and fairly simple, but it's not terribly reliable. I can come up with other data sets that have a range of 11 that you might say are more or less spread out than that. For example, that data set there still has a maximum of 18 and a minimum of 7. So it has a range of 11. But would you say it's the same amount of spread out? Probably not. Let's take a look at the two. So 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'm going to plot this set above. So there's 7, 12, 12, 13, 18. I'll plot this set below. So I've got 7, 11, 7, 9, 10, 11, 18. Not a lot of difference, but I would say the green ones are a little bit more spread out. So how do I distinguish between sets that are similar, that have the same range, but maybe not the same spread? I'm going to put up a pretty obvious example here. I'm going to do it like this. Let's say we have 7, let's do 10, 11, 13, and let's see here. We do 19. That'll work out well. Or 7, 8, 12, come on. There it is. Oh, let's see what I want here. I'm going to change one number here. I'm going to change this 12 to a 13. So 7, 8, 13, 18, and 19. Again, I would say there's difference in how spread out they are, but they both have a range of 19 minus 7, or 12. So what we're going to use for that is something called the standard deviation. Now, the standard deviation involves 6 steps, and each step has a name. So let's go through this 6-step process. Step 1 is to find the mean. So let's use this top set of numbers, and let's find its mean. 7 plus 10 is 17, plus 11 is 28, plus 13 is 41, plus 19 is 60. Divided by 5, because there are 5 numbers in the list, so that mean is 12. Step 2 is to subtract the mean from each number. So I have 7, 10, 11, 13, and 19. I'm going to subtract 12 from each of those. 7 minus 12 is negative 5. 10 minus 12 is negative 2. 11 minus 12 is negative 1. 13 minus 12 is a positive 1. 19 minus 12 is 7. This list of numbers I got here is called the deviations, sometimes called the deviations from the mean. Now, if I wanted to double check myself here, things are just disappearing on me all over the place here. If I wanted to double check myself, I could add these up and check. They should add up to 0. Now, that's not part of the calculation, but if you wanted to make sure you're doing things right, that would be how to do it. If that doesn't add up to 0, that generally means that either you subtracted one of them wrong or the mean is incorrect. A lot of times if you have to round the mean, that won't quite be 0. Step 3. Square each deviation. So to square a number, negative 5 squared. When you enter that in your calculator, make sure you put it in parentheses. Because if I just type in negative 5 and hit squared, it's going to try to tell me it's negative 25. We know that's not true. Negative 5 squared is negative 5 times negative 5. A negative times a negative has to be positive. You have to put it in parentheses like that. Negative 5 in parentheses and then squared. Tells you that it is 25. Negative 2 squared is 4. Negative 1 squared is 1. Again, all these numbers have to be positive because anything squared is going to be positive. 1 squared is also 1. And 7 squared is 49. This list of numbers here is called the squared deviations. Real creative, right? Step 4. Step 4 is to find that total. Add those up. So 25 plus 4 is 29, plus 1 is 30, plus 1 is 31, plus 49 is 80. That total is called the sum of the squared deviations. Now I'm going to pause here a second, make sure everybody's caught up. Step 5 is where it gets a little tricky. Step 5 is to divide by n minus 1. For this data set, n equals 5. Where did I get the 5 from? There's 5 numbers in the list, right? N equals 5. So n minus 1 is equal to 5 minus 1, or 4. So for this data set, for step 5, we would divide by 4, because n is 5. 80 divided by 4 is 20. This number right here is called the variance. That's a big one. The variance is often used in some of our statistical tests. The variance is used for some of the calculations that we do in them. Then finally, step 6, the last step, is to square root the variance. Now, don't confuse squared and square root. Up above, we squared it times itself. Down here, we're doing the square root. So the square root of 20 is going to be 4.47. That is the standard deviation. The standard deviation describes, on average, how far each number is away from the mean. Any questions? Now, I'm not mean enough to give you one example and leave you hanging. Let's go back and do the second data set. So 7, 8, 13, 18, and 19. But you guys are going to tell me what to do. Where do we start? Find the mean. So here we got 7 plus 8 is 15, plus 13 is 28, plus 18 is 46, plus 19 is 65. We divide by 5 because there's 5 numbers in the list. Gives us a mean of 13. What is step 2? Subtract the mean from each number. So I've got 7, 8, 13, 18, and 19. We are going to subtract 13. Seven minus 13 is negative 6. Good. 8 minus 13 is negative 5. 13 minus 13, of course, is 0. 18 minus 13 is 5. And 19 minus 13, 6. What are those called? They're called the deviations, or the deviations from the mean. Very good. They should add up to 0. We don't have to do that. It's not really part of the process. But if you wanted to check, that's one way to do it. But step 3, square each deviation. We're going to square them. Negative 6 squared is 36. Negative 5 squared, 25. 0 squared, 0. 5 squared, 25. And 6 squared, 36. Step 4, add them up. Find the total. Those add up to 122, I believe. Step 5. Divide by n minus 1. So n is 5. N minus 1 is 4. So we divide by 4, which is going to give us 30.5. That's called the variance. There you go. What's our last step? Square root the variance. Square root of 30.5 is 5.52, and that is the standard deviation. Now up above we had 4.47. So that's telling us that this data set is more spread out than the other one. Any questions? Anybody's brain a total meltdown yet? Okay. Let's look at a frequency table. So we're looking at students and how many classes they have. Now, if they have 0 classes, they're technically not a student right now. So nobody has 0 classes. And let's say we've got students that have anywhere from 1 to 5 classes. Of the students we surveyed, let's say that 5 of them had 1 class. 8 had 2 classes. 14 had 3 classes. 8 of them had 4 classes, and 7 had 5 classes. What this really is a list of numbers like this. There's 1, oops. How many 1s are there? There's 5 of them. 1, 1, 1, 1, 1. How many 2s are there? 8. 2, 2, 2, 2, 2, 2. How many 3s? Yeah, I'm not going to list out 14 3s, but you get the picture. It's individual numbers, we're just grouping them together. So rather than writing out 5 1s, we just say 1 and it put on a frequency of 5. So it appears 5 times. To find the mean or the median of this, let's start out by finding the median. The median, remember, is the middle. And the position of the median is n times 0.5. Well, what's n here? A lot of people would mistakenly say n is 5, but that's not true. Yeah, the n is the total frequency. I have to add those all up. So 5 plus 8 is 13, plus 14 is 27, plus 8 is 35, plus 7 is 42. That adds up to 42. So n is 42. So that position is 42 times 0.5, which is 21. That's a whole number. So that tells us what? Our median is between that one, the 21st, and 22nd number. So let's go up here. 21st and 22nd number. Well, the first through the fifth number are ones, aren't they? The 6th through 13th, where did I get 13 from? Yeah, 8 plus 5 is 13. Those are all twos. The 14th through the 27th are all threes. But we're looking for the 21st and 22nd. Those are in that range, aren't they? The median of this is 3. How about finding the mean? To find the mean, remember the first step is to find the total. To find the total, adding them all up, here what we have to do is we have to do the class, I'm going to call that x, times the frequency. There's 5 that have one class. That's a total of 1 times 5, or 5 classes. There's 5 ones. I can add the other 5 times. There's 8 that have 2 classes. So 2 times 8, the total is 16 more classes. Again, that would be from adding up these 8 twos. That would add up to 16. There are 14 of them that have 3 classes, so that 3 occurs 14 times. 3 times 14 is 42. 4 classes happens 8 times, so 4 times 8 is 32. And 5 classes happens 7 times, so 5 times 7 is a total of 35 classes. So the total number of classes taken is found by adding that up. It's at 21, 63, 95, 130. There's 130 total classes. We take that total divided by n. N is 42. 130 divided by 42. 42 isn't the median, that's n. That's the number of items that are there. There's 42 total items. So that's 3.095. That's the mean. This process, by the way, would be extra credit on a test. I would make you do this. This would be at the end of the test for extra credit. It wouldn't be part of the graded portion of the test. Won't be quite that mean to you. You guys would really have to upset me. Yeah, the median or the mean, you'd really have to upset me to make me force you to do that on a test. So be nice to the teacher. Did you upset me? Okay, so let's look at number of cars. Let's say we got some people that have 0, some that have 1, some that have 2, some that have 3, and some that have 4. We have 3 people that have 0, 13 people that have 1. Well, let's say that we have 8 people that have 2. Let's come up with a number that works nice here. You know, there's been times where I could. Right now, it's not going so well. And let's have 5 that occur 3 times and 1 that occurs 4 times. Hopefully, this works out well. To find the standard deviation, the first step is to find the mean. So let's do that process of finding the mean. What's my first step to find the mean? I have to add them all together. There's 2 things that I have to add together, though. I have to find the n, my total. I add those up. What do I get? Should be 30, right? Careful. That's just my total frequency. That's n. That's what I have to divide by to get my mean. I've got to find my total yet. My total is the cars times the frequency. There are 3 zeros. How many total cars is that? That's 0, yes. There are 13 people that have 1 car. How many total cars is that? 13. 8 people that have 2 cars? 16. 3 people that have 5 cars. That's 3 times 5 is 15. And 1 person has 4 cars, which is, oops, that should be a 1, not a 4. That's 4. So we add those up. Is it 49? 48. Is that right? So the mean is the 48 divided by the 30, or 1.6. N is the 30. That's what we divided by. The mean is 1.6. Step 2 of a standard deviation is to subtract the mean from each number, right? Number minus mean. 0 minus 1.6, negative 1.6. 1 minus 1.6, negative 0.6. 2 minus 1.6, 0.4, right? 3 minus 1.6, 1.4. And 4 minus 1.6 is 2.4. Step 3 is to square them. Yeah. Negative 1.6 squared is 2.56. Negative 0.6 squared is 0.36. 0.4 squared is 0.16. 1.4 squared is 1.96. And 2.4 squared, 5.76. Now, the fourth step is to add them up, but there's a problem here. These numbers don't just occur once each, do they? This deviation occurs 3 times. So we have to do 2.56 times 3. So these are the squares. We have to do the square times the frequency for each. This 0.36 occurs 13 times. What's 0.36 times 13? 4.68. The 16 occurs 8 times. That's 1.28. The 1.96 occurs 5 times. Was that 9.60? 9.80, isn't it? And the 5.76 occurs once. So now to get the total, I have to add those numbers up. Oh, what is that? 9, 15, 17, 25, 32, carry the 3, 10, 14, 15, 24, 29.20, is that what you get for total? You messed up? You got it. That's good? Okay. So that's the total. Step 4, or step 5, I should say, is divide by n minus 1, right? Well, that's going to be 29.20 divided by n is 30, so we're going to divide by 29. 1.007. That, by the way, would be the variance, n minus 1. N equals 30, so n minus 1 is 29. So 1.007 is the variance. The standard deviation is the square root of the variance. So square root of 1.007. Oops, try that again. This would also be an extra credit question. So that would come out to be let's just do this, 1.003. Word is going to act up on me, which it's time to, you guys have suffered enough anyway. There will be a new homework assignment due for next week. There is no quiz this week. So just a homework assignment due for next Wednesday.